Hello again. We're discussing the introduction to molecular mass determination by freezing point depression experiment. This experiment is designed to illustrate one of so-called colligative properties. Hopefully you talked about these in lecture. They include freezing point depression, boiling point elevation, and osmotic pressure. All these properties have one thing in common. Their magnitude depends only on the number of particles of solute. These are properties of solutions only. So when you hear colligative properties, think solutions. So solution, of course, is a system that contains at least two components, solvent and solute. Turns out adding solute to a solvent, creating a solution, alters some of these properties such as freezing point and boiling point. And that's why we're looking at these properties. So the goal of the experiment here is to find molar or molecular mass of an unknown solute in solution. Freezing point depression is found as freezing point of solvent minus freezing point of a solution. The word depression is key here. Depression, of course, means lowering. So what we expect to happen is when we create a solution by adding a solute, the freezing point is expected to decrease or drop. So freezing point of the solution is expected to be lower than that of the solvent. Therefore, when we're subtracting lower value from the higher value, we should get a value that's greater than 0. Thing to keep in mind is delta TF cannot be negative. In the second lab quiz, you will be given a problem where you'll have to find freezing point depression, and it's important to subtract freezing point of solution from that of solvent, not the other way around. And if you get a negative value here, it will be considered incorrect and points will be deducted. Freezing point depression, being a colligative property, is proportional to molality of solution based on this equation here. This is the main equation in this whole topic. Magnitude of freezing point depression is found as Kf, which is a constant for a given solvent, times molality. Molality, of course, is found as moles of solute per kilogram of solvent. Again, molality is not the same as molarity, so be sure to distinguish between the two. So molality, of course, can then be expressed as delta TF over Kf, and then moles of unknown solute can be found as molality times kilograms of solvent. Another important thing when doing these problems is to clearly establish from the very beginning which substance is a solute and which one is a solvent, so you don't get them confused. And so moles of solute eventually can be figured out as delta TF over Kf times kilograms of solvent. This leads us to our final equation that we can use to find molar mass of the unknown. Molar mass of any substance is found as its grams over its moles. So if we take grams of solute that we use to prepare the solution divided by moles of solute found up here, we can then determine molar mass of the unknown in grams per mole. So I arranged it in this equation here. Molar mass of unknown solute is equal to grams of solute times Kf divided by kilograms of solvent divided by delta TF. This is equation 7, page 71. So for the quiz, you have two options. You can either just remember the simple derivation that I did to show how molar mass can be found step by step using delta TF and molality, or you can just use equation 7 right here. The quiz will be closed book, so you have to memorize this equation. As far as the procedure is concerned, I'm not going to discuss it in detail because you are not going to do it yourself. I just wanted to show you what the experimental setup would look like. And the substance that's used in this experiment as a solvent is called tert-butanol. I will show you its chemical structure in a second once I raise the screen. This, of course, being a liquid, would be expected to be in a bottle, and it is, but I'm not sure if we will be able to show this to you. I just went and grabbed this off the shelf in the prep room, and hopefully you can see it says terbutanol. But the interesting thing about this substance right now is pretty much completely, totally frozen. I'm gonna open it and we'll see if we can peer inside the bottle. So it's an interesting substance which happens to be frozen at room temperature. In fact, this tells me that the temperature in this room right now is probably around 23, 24 degrees Celsius, or definitely below 25, because the expected freezing point of this pure substance is right around 25 degrees Celsius. It says so right here on the label. It says freezing point 24.9. I'm not sure if you'll be able to see it. It's okay, it's fine. So what we would do in the lab for you is TAs would place these bottles in a warm water bath in a large beaker to allow it to melt so that you could pour it. So what you would do is you would take a large test tube that we would provide like this. You would weigh the empty test tube and record its mass. You would then pour a certain amount of terbutanol in here, obviously after it's been melted and warmed up. And then you would weigh the test tube again so that you would know the exact mass of terbutanol in your test tube. You would then measure freezing point of pure solvent by placing this aluminum wire with a loop on end that's your stirrer inside the test tube, and make sure it can be moved up and down like this. You would follow temperature changes with a temperature probe that's attached to the data logger. So you would place the loop of the stirrer right around the temperature probe like this, and you would lower this whole assembly into ice water mixture. In fact, for terbutanol, it's basically water maybe with a couple of pieces of ice, so that you can gradually and slowly cool it and obtain your cooling curve right on the screen of the data logger that would be set up in the graphing mold. And then you'd be able to print that cooling curve, and we're going to discuss what this cooling curve would look like in a minute. Then, after you did this a couple of times to get 2 trials in for your pure solvent, you would be assigned a solute, which could be either a liquid or a solid. You would either weigh this certain amount of solid, close to 2 grams if it's a solid unknown. If it was a liquid unknown, you would get help from TAs measuring exactly either 1 or 2 milliliters of specific unknown into here to create a solution. And then you would add more ice, significantly more ice, to your water bath. Because remember, solution would freeze lower than the solvent, so you need more ice to make your ice bath colder. And you would then place the assembly into the ice water bath, making sure that the entire solution in this instance is covered with water in the beaker. And then you would begin freezing your solution and find freezing point of the solution based on the cooling curve it gives you. And then you would do the necessary calculations. So having shown you this, there's a couple more things I'd like to point out in this handout before I show you the cooling curves. So a couple of things you need to know. If you were doing this, you would only do parts 1 and 3. You would not be doing part 2 where KF is found. Instead, you would use this value for KF given here in the note. So for terbutanol, KF has a value of 7.94 degrees Celsius times kilograms over moles. So this would be the KF you would use for all calculations in this experiment. And also, as far as unknown is concerned, you of course will be told which unknown was used to get data that you will be provided. For solid unknowns, we weigh close to 2 grams, so you'll be given exact mass of the solid unknown, and you'll be told whether it was unknown number 2 or number 4. The liquid unknowns, we have a number 1 and number 3, and you will be told which unknown you had. And for unknown number 1, expected volume used to prepare a solution is 2 milliliters. For unknown number 3, the volume is 1 milliliter, using micropipette for greater accuracy. So what I'd like you to do, once you have all the data provided by your TAs, and you know which unknown was being used for the solution, you will use data provided to find freezing point of solvent and solution, and then find freezing point depression and molality, and eventually molar mass of the unknown. These here are 4 substances used as unknowns. They're scrambled, so they're not in order, they're numbered. And they give you all the actual or accepted values for molar mass. So what I'd like you to do for your post-lab is I'd like you to try to identify the unknown based on which molar mass that you find experimentally matches closest to one of these 4 values. And so for your report, you will only be turning in data sheet 4 and the post-lab. And I guess copies of the cooling curves, possibly. I will let you know exactly at this point. I'm not sure how we're going to do this. So now I'd like to pull up the screen and do a quick review for you, just to make sure you're clear on this. So the experimental procedure involves first measuring freezing point of pure solvent, substance called torbutanol. This is its chemical formula. The expected freezing point for pure torbutanol is right around between 25 and 26 degrees Celsius. So the cooling curve that you would see would look like this. We usually start cooling right around 28 degrees. We want to make sure we're high enough not to miss the actual freezing point. So we start high, we put the test tube in warm water a little bit so its temperature rises a little bit. And then at around 28 degrees, we place the test tube with our pure solvent, with our torbutanol, into the ice water bath, and we begin cooling. We notice temperature dropping, briefly coming back. This is the area called supercool, and then sort of level off at a more or less constant value right around 25 degrees. So if we draw the horizontal line parallel to x-axis over to y-axis, we find the freezing point of the solvent is right around 25 degrees. It may be a little bit below because torbutanol happens to absorb moisture really well, and of course any moisture that is absorbed will act as a solute, and so it may lower the freezing point of torbutanol a little bit, but we do expect it to be right around 25 degrees or so. And then, skipping the part of the experiment where you would have to find KF value, we're going to look at cooling curve for the solution. So taking the unknown, again, either liquid or solid. For solid, close to 2 grams. For liquid, depending on which unknown it is, either 1 milliliter or 2 milliliters. By the way, densities of the unknown liquids, I believe, are given in the notes. I skipped that earlier, but I think these densities are provided. So you can find mass of the unknown liquid based on volume and density, sort of like you did in the Prelab. Here, the freezing point is determined starting at the lower temperature than before. So for pure solvent, we start at around 28 degrees. Here you start at around 23 to 24 degrees, you start your cooling. And then you continue cooling. You also see, most often you do see supercool. You may or may not see supercool, it's not that critical. But then what happens is, after briefly coming back, temperature slowly decreases unlike in the earlier curve that we saw for the pure solvent, here temperature never stays constant, it gradually decreases. There's clearly a little bit of a negative slope right here. And this is due to the fact that this is a two-phase system. It's not a pure substance anymore, it's a solution containing a solvent and a solute. And there's obviously a lot more solvent in the solution than solute in most cases. So what happens here is solvent is the one that starts freezing first, and the solvent is turning solid. Think about what happens in the remaining liquid. In the remaining liquid, you now have less solvent left because some solvent has become solid, which means there's more solute per unit of solvent, which means concentration is greater. Remember, the greater the concentration of the solution, the lower the freezing point. And so, because solvent is sort of being frozen out, the concentration of solute in the remaining liquid is increasing, which causes the freezing point to become gradually lower and lower. That's why you're seeing negative slope. Bottom line is, if you have a cooling curve like this, you would then extend the sloping line over to the initial part of the curve, and then you'd go straight over to y-axis to find freezing point of your solution. So in my case, by the way, these are totally made up numbers, so don't read too much into it. I just kind of wanted to show you schematically what you can expect. So freezing point of the solution in this case would be expected to be around 18 degrees. Again, once you find your freezing point of solution and freezing point of solvent, you can find freezing point depression, and based on freezing point depression and Kf value given for terbutanol in the notes, you can then determine molar mass of the unknown.